Welcome back. This episode is about the binomial theorem. This is a very nice theorem about binomial coefficients. It gives us a new perspective on these numbers. So we've already seen quite a few such perspectives, right? Last episode we saw an exact formula for them in terms of factorials. We've also seen their definition in terms of counting subsets, and we've also seen their connection to Pascal's triangle. And this actually gives us a connection to polynomials, of all things. Okay, let's get to it. So first, a bit of notation. If you haven't seen this, this is essentially what's called summation notation. So this is a way of, when we have this kind of ugly looking sum with dots and stuff that goes up to n, and we don't know how big n is, we can often write it more succinctly in terms of this Greek letter sigma, right? And the way you can kind of read this is that this is the sum from k equals 0 to n. And here I've just written that kind of ck as like some kind of generic thing, but it'd be helpful to maybe see a few examples of this if you haven't seen it before. For example, k equals 0 to n of k squared. It's the sum from 0 to n of k squared. So it's 0 squared plus 1 squared plus 2 squared, so on and so on, up to n minus 1 squared plus n squared. Right? And, we can have a definite value as well. Like you can do k equals 0 to 2 of k cubed, for example, is just 0 cubed plus 1 cubed plus 2 cubed, right? So this is summation notation. It makes certain things a lot easier, and we'll use it later on. It's helpful to get familiar with it. So into the main thing here. Let's look at Pascal's triangle, everyone's favorite. And I'll just kind of come back to this in a second. You'll see why. Let's expand the following polynomials. Okay, x plus y to the 0 is just 1. No surprise there. X plus y to the 1. I'm going to suggestively write this as 1x plus 1y. Again, hopefully pretty uncontroversial there. What about x plus y squared? Just remembering our FOIL. This is x squared plus 2xy plus y squared. Again, I'm writing the ones for a reason that you'll see. X plus y cubed, this one requires a little bit more work. This is x plus y times x squared plus 2xy plus y squared, right? Because we just calculated x plus y squared above. Which gives us x cubed plus 2x squared y plus xy squared plus x squared y plus 2xy squared plus y cubed. Oh my goodness. What are we left with? We're left with, I see 1x cubed term. I see 3 x squared y terms. I see 3 xy squared terms. And I see 1 y cubed term. Okay. That wasn't the prettiest. But now, let's look at these coefficients. We have a 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Now, scrolling up a little bit, this is just Pascal's triangle. Now, that's pretty cool and pretty surprising. I definitely would not intuitively think that these polynomials give you the coefficients of Pascal's triangle, which are, of course, the binomial coefficients. So this suggests a wider pattern, and the wider pattern does in fact hold. You can expand out x plus y to the 4, and you can see for yourself. I'm not going to do that here. So what is the general pattern? It's the binomial theorem. It gives essentially a very succinct way to find the coefficients in this polynomial, x plus y to the n. So again, maybe you're not so comfortable with summation notation, I'll just write this out in its expanded out form. This is n choose 0, x to the 0, y to the n, plus n choose 1, x to the 1, y to the n minus 1, and so on, up to n choose n, x to the n, y to the 0. This is the general pattern. So you can imagine how this would be very helpful, right? You can already see, even up here, that we have x plus y cubed. This already takes a little bit of work to just expand out by hand. You can imagine x plus y to the 5, 6, x plus y to the 20 are just enormously complicated to do by hand. And this formula gives us a very convenient way to evaluate these polynomials, which is very nice. And again, also gives us a kind of new angle and binomial coefficients because, at first glance, you'd think, what on earth are these even doing here? So let's look at the proof. What it essentially boils down to is, let's say we have our x plus y to the n, right? It's just repeated multiplication of x plus y, right? We have x plus y times x plus y, yada yada, x plus y, where, all in all, we have n of these terms. Okay. And we have coefficients. In particular, we have sum from k equals 0 to n of, well, I guess I'll put a question mark here for now, x to the k, y to the n minus k, right? We do know that when we expand out this polynomial, we'll get something of this form, where we have this x to the k, y to the n minus k. The question is, what's the coefficient, right? That's really the big question here. What is the coefficient? So, okay. Let's think about what this coefficient means, okay? Essentially, I'll write this as this question mark. What does question mark equal? Question mark is the number of ways to get, I'm being a bit vague here, but it's the number of ways to get, maybe I'll phrase this, the number of ways to get k x's and n minus k y's from this product, right? From this x plus y to the n. Okay. So maybe this would be best illustrated with an example, right? If we have our x plus y cubed, which is x plus y, x plus y, x plus y, you'll recall that this is x cubed plus 3x squared y plus 3xy squared plus y cubed, right? So this 3, I'm claiming here that 3 is the number of ways to get 2 x's and 1 y. Okay. Well, how can we do that? We can get 2 x's by choosing these two and choosing this one, right? That gives us 2 x's and 1 y. That's one way to do it. I think I'll just kind of undo this. We can also do this, right? And we can also do this. So what are we really doing here, right? What is the number of ways to get kx's and n minus ky's from x plus y to the n? Well, what's this process here? We're essentially just choosing, I could say number, this question mark, it's the number of ways to choose, we could say, k of the x plus y's. I'm being a bit vague here, of course. I could put quotation marks around all of this. Choose k of the x plus y's. In this case, remember, we're choosing, let's say, 2 of them to be x's. So choose k of the x plus y's to be x's, right? Very vague here. And n minus k of the x plus y's to be y's. Okay. Being very vague here, but I hope the example I went through earlier makes it a little bit more clear what's going on here, right? Essentially, each coefficient corresponds to choosing k x's and choosing n minus k y's to multiply. Okay. But then what is this, right? This is just, each of these choices is really just number of ways to choose k things from n things, right? That's all this really is, right? You're just choosing k of these things to be your x's. Once you've chosen the x's, the y's are just whatever's left over, right? So maybe in this example, again, I can kind of go through this. 3 is a number of ways to get 2 x's and 1 y. This is really 3 choose 2, right? You're choosing the 2 x's. Let's choose the 2 x's. And again, the 1 y here you don't really have to worry about because once you choose the x's, the y's are just whatever's left over. Okay? But of course, what is the number of ways to choose k things from n things? This is just n choose k. So going back up, that means that x plus y to the n, right? This equals the sum from k equals 0 to n, question mark x to the k, y to the n minus k, and question mark is n choose k, right? This is exactly the result we want. And so we're done. Okay. So maybe intuitively you can kind of convince yourself the reason why binomial coefficients show up in these polynomials, which I think at first, again, is a very non-obvious fact, is from this behavior of multiplying out, right? When you want to get x squared y, you choose 2 x's and you choose a y, right? And because there's 3 ways to do that, that's where this 3 comes from. Okay, that's the intuition I want you to have for this. So, okay, very powerful result. We can use this with polynomials all the time. A very quick corollary is just plug in y equals 1. So, binomial theorem, right? What is the binomial theorem? X plus y to the n is the sum from k equals 0 to n of n choose k, x to the k, y to the n minus k, right? If we just plug in y equals 1, what do we get? Well, we get x plus 1 to the n equals the sum from k equals 0 to n of n choose k, x to the k, 1 to the n minus k, which is just 1, so this is just x to the k. Okay, you may wonder why I even kind of bothered writing this down. It's because it's sometimes useful to have. It's maybe just nice to remember that x plus 1 to the n has this nice property that the coefficients are literally just binomial coefficients. That makes this a kind of nice polynomial. But let's get into some examples now to see how this is useful. So x plus y to the 4. You can try expanding this out by hand, and I'm sure you can do it, but it won't be very much fun. So let's do a more fun way. Let's just write a Pascal's triangle, right? We have the 1, we have ones on the diagonals, right? We have a 2 in there from some things above it, right? I'm just kind of writing out the triangle here. And I'm going to go up to, let's see, we need up to this row, yes, because this row essentially corresponds to x plus y to the 0, right? This is what we saw in our earlier example. This one corresponds to x plus y to the 1. So you can kind of like label the rows in this way. Like this is row 2, this is row 3, this is row 4, right? And so, okay, x plus y to the 4, this is just, I mean, I can write out the binomial theorem, but again, the nice thing about Pascal's triangle is, let's just do this very quickly. This is just x to the 4 plus just reading off the coefficients, right? Oh, sorry, I should write this as x to the 0. Yes. And now just increase x by 1 and have the coefficient in front. So x to the 1. Sorry, this should be, you know, it's never too late to just write out the binomial theorem just to make sure that you have it correct. It's 4 choose k, x to the k, y to the n minus k. So what do we get from Pascal's triangle, right? We have x to the 0, y to the 4, plus 4, x to the 1, y cubed, plus 6, x squared, y squared, plus 4, x cubed, y to the 1, plus 1, x to the 4th, y to the 0. Okay? So, okay, I messed up a little bit there, but I think you can still agree this is a lot easier than expanding things out by hand. Okay? So yeah, and this gives you like a very quick way to find out. For sort of small powers of n, you can use Pascal's triangle to compute the polynomial in this way, right? Okay, one last example. What is the coefficient of x to the 8 and x plus 2 to the 10? Now, this is one that you would truly be hopeless doing by hand. I sure wouldn't want to do it, but thanks to the binomial theorem, this question is actually pretty straightforward. What is x plus 2 to the 10? It's the sum from k equals 0 to 10 of n choose k, x to the k, 2 to the n minus k. I should write this n actually as, well, of course, this n here is just 10, right? Okay. So where's our x to the 8? Our x to the 8 is when k equals 8, of course, right? But then what does this become when k equals 8? This is 10 choose 8, well, x to the 8, 2 to the 10 minus 8. So the coefficient of x to the 8, we'll just write this as the coefficient of x to the 8 is just 10 choose 8, 2 to the 10 minus 8. And maybe just for fun, let's calculate what this turns out to be. This is 10 factorial over 8 factorial, 2 factorial. This is our formula from last time, right? 2 squared. Remember, 10 factorial is 10 times 9 times 8 factorial. Again, over 8 factorial. 2 factorial is just 2 times 1, right? Times 4. Okay, our 8 factorials cancel. That's the scary part. We have 10 times 9, which is 90, over 2 times 4. 90 over 2 is 45, so 45 times 4, which is 180. Okay, so there you go. That's your coefficient of x to the 8. I mean, yeah, you can try to expand this out by hand. You'll have a very tough time doing so. Okay, so this episode I think has been a little more tricky, at least for me, but I think it's very instructive and it's just a very nice theorem. A very surprising place that binomial coefficients show up, and very useful as well for calculating these kind of questions. Okay, great. Thank you for watching.